Welcome to everyone. Previous class we have discussed on representation of groups that we used to represent two ways, either in reducible representations, another is irreducible representations. So today class we will study about of character tables. So we have discussed only reducible representations and irreducible representations we have not discussed. So that we will discuss after completion of the character tables. So today we will start the topic character table. So if I say that what is the importance of character tables and why you are studying this, so it is character table helps to show the applications of group theory. It helps to show the applications of group theory, or you can say applications of point groups. So now next, so what is the character tables it contains? So how the character tables look like? If I say the character tables has the character table has two rows that I represent as R1 and two columns. Sorry, and four columns it has, and four columns. Okay, so you know that this means rows. These represent these are rows and these are columns. So these are rows and these are columns. Okay, so now how the character tables look like? It has two rows and four columns. So character tables is look something like, let's say two rows, and I have the two rows here I will draw, and I have that four columns. So this is one columns, and let's say for two rows I will draw two rows, and I will write first I will draw four columns. So it has one columns, two columns, three columns. So four columns and two rows. This is row 1, this is row 2, and four columns. This is column 1, column 2, column 3, column 1, column 2, column 3. Another we have that column 4. So four columns are there and two rows are there. This one I can draw like this, and it has the point group table. Character tables look something like this. So two rows and four columns. Let's say this I will put 1, and this is 2, and this I will put 3, and this is 4, and this is 5, and this is 6. Okay, so in this 1 2 3 4 5 6 we will have some variables or some numbers. Let's say what things are there in 1, what things are there in 2, what things are 3, what things will be there in 4, and what things will be there in 5, and things will be there in 6. So if I says that 1, in 1 it will have implies notations of point group. So first one we will write the Swann-Fly notations of point groups. So I will write that. So one we will write write Swann-Fly notations of point group, and what we will write at 2 at 2 at 2 we will write uh, 2 we will write the symmetry elements of this point groups. So at 2 we will write the symmetry elements of that particular point groups, whichever we written, symmetry elements of that particular point group. And what will be in 3 will write 3 will have that Malkin notations of irreducible representations. At 3 will write that Malkin notation of irreducible symbol. And what we will write in the 4? At 4 we will write 4 we will write the characters of irreducible representations. So here we write characters of irreducible representations. So here in 3 we will write the notations, and in 4 we will write the characters of irreducible representations. And what we will write on B and 6, and in V we will write the transformations properties of translational rotations, translational or rotational equations. Okay, so and 6 we have write the quadratic equations, and 6 we will write quadratic equations like x square, y square, and x y x z, like that. Okay, how we'll write we will discuss. So these are the 4 things, and for our exam point of view, this is important, and this is important, this is important, and this is important. This will be actually the tables will given in the exam itself, but this 1 2 3 4 we should know it. Okay, so we will discuss one by one how to represent and how to write the character tables. So let's discuss. So let's take the examples of water. If I take example, let's take water. So for this water molecules, what the point group it has? The point group is C to B, and symmetry elements, let's say this is X, this is Y, this is Z. Then this is having, we already discussed, C2Y first E plus C2Y plus sigma yz plus sigma xy. This is the water molecules it has. Okay, so that we already discussed. So what you write in the character tables, first in one you write the Sonipal notation of the point group. Means if I draw here the tables like this is the table. So this is the half, this row 1, this is row 2, and this is column 1, and we have column 2, this is column 1, this is column 2, and this is column 3, and we have another column 4. So here what we write, first part we write the Sonipal notations of the point group, means the point group. So here our point group is C2B, and in part 2 what we write, symmetry elements of the particular point group. So what are the symmetry elements here? 2. Okay, in 2 I will write symmetry elements of the particular point group. So symmetry elements for water we have E we have, C2Y we have, sigma YZ we have, sigma XY we have. So I read these elements. After that, in 3 what I write, Malkin notations of irreducible representations. So that Malkin notations, so I write like, so let's say irreducible representations, the notations like IR1, I don't know. So IR, that's why I write any value like IR1, IR2, you may write. So IR, why I am writing irreducible, irreducible representation. So shortcut I am writing IR1 because now I don't know the value. So after know the value, I will put the exact value. I will simply the notations IR1, IR2, IR3, IR4 dot 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 dot. Okay. I don't know how much I have to put from the, for time being I don't know. Maybe IR5 also come, IR6 also come. Okay. So this will be there, and in third what you will write, Malkin notation of irreducible representations, and fourth write the characters of irreducible rotations. So the characters I have to write here. So we don't know the characters now, so simply we write, let's say K, L, M, N1, K2, L2, M2, N2, and K3, L3, M3, N3, K4, M4, sorry, K4, L4, M4, N4. Maybe I write K5, L5, M5, N5. I don't know that whether IR4, IR5, but so after rules we will say that what we have to write. So now simply I am writing the same, and this also I don't know for the time being. Okay, so whatever that written, that's what I'm just doing. Now after that what I wrote, write the transformation properties of the translational rotational equation. So here we have to put the translational and rotational values. Translational and rotational means like x, rx, like that value you have to put here. Here that any quadratic equations that the characters has, point group has, so here maybe x square, y square, r, like that value will come. Okay, so this is what that this 6 point says, that these things should include in the character table. Okay, so now next we'll so here for this is the part 1, this is part 2. So part 1 and part 2 is clear, that here that any point group notations will be there, Sonipal notations, here the symmetry elements is there. That this part 3 we don't know that what the values, and this part 4 we don't know what the value, and this also we don't know. So after studying the rules we will understand this. Here also we don't know now for the time being. Okay, so Mm, so to write that, so to write the character table, write the character table, we should follow, we should follow the great orthogonality theorem. That is, we can say GOT theorem. So this theorem, some postulates we have is there. That postulate we have to follow to write the character tables, or sorry, to write that this for one. So to write the character tables, we have to follow the great orthogonality theorem, that is GOT. So this gives some postulate. That postulate we have to follow to write the character tables. So what are the postulates GOT gives? The past postulates, it has past postulate. What it says that the number of irreducible representations, irreducible representations, or irreducible, the number of Malkin notation of irreducible representations, irreducible notations is equal to the number of classes of the point group. So past one, what it says that the number of Malkin notations of irreducible notation, the number of Malkin notations of irreducible, the number of Malkin notations of irreducible of character of, I write something wrong, sorry. But the point says that the number of Malkin notations of character tables is equal to the number of class of the point group. Means that the number of Malkin notations, this one, this is the Malkin notations. So this notations is equal to the number of classes. Yes, here that 2, 3 you have explained like that. The Malkin notations of irreducible symbols. These symbols, the number of Malkin notation by irreducible symbol is equal to number of classes of the point groups. So how many classes we have? 4 class. This is 1, 2, 3 and 4 class. So here also the notations has to be up to 4 only, not 5 and 6. That the past postulate says. Okay. So similarly, if you take the examples of water, then C2B here has E, C2, Y and sigma YZ and sigma XY. Then how many classes we have? 4. So here also I have to write IR1, IR2, IR3 and IR4, not IR5, because how many classes? The same number of notations of irreducible symbols will be there. Okay, so up to 4 class, so 4, up to 4 will be there. This is the first postulate. It says this is the postulate 1. And what the second postulate says? Second postulate says that the dimensions of identity element or identity symmetry or identity operations, I say identity operations is equal to the order of the point groups. That the second postulates. This is postulate 2 says. But postulate says that the dimensions of identity operations is equal to the order of the point groups. So this identity means, let's say for water if take C2B EE C2Y sigma YZ sigma XY, and here we have IR1 IR2, here we have IR3, here we have IR4. So previously what we are saying that this is the E. So whatever the symmetry elements of these operations, these are the, you know, that character of identity elements is equal to the dimensions. So here that this value will be, so this is the dimensions of identity. So what we say that here that we have written these values k1 k2 k3 and k4. This one k1 k2 k3 and k4, this is the E shows that characters of E shows that dimensions of the group. So this these elements of E is equal to the order of the point groups. So we know that order of point group C to B. So we know C and B as the point group of 2n. Here n is 2, so 2 into 2, that is equal to 4. So this is the order of C to B, that is equal to 4. So now, so this the dimensions of or the symmetry of identity is equal to the order of group. So I can say that k1 plus k2 k3 plus k4. Just a minute. C3 if we have, then on that case what we have E to C3 is sigma B and H1 to B, then it have 1. This is yeah. What is said that the postulate is, sorry for that wrong, postulate is that the summation of square of identity elements is equal to order of the group. Okay, this is the second postulate. So here that order of the group is 4. So after adding this, we get this square. If we square it off, then we should get order of the group, that is 4 for water case. So this, for getting 4, that all has to be plus 1 because we need the 4. So this has to be 1 square plus 1 square, 1 square plus 1 square, then we get 4. It means 1 1 1 1 equal to 4. Okay, so this all the value has to be 1 to get 4. If anyone is -1, anyone is +2, then we will not get 4 because 1 that square of summation of the identity element is equal to the order of the group. So for that, here all has to be 1 for C to B case. This is 1, this is 1, this is 1, this is 1. Okay, this is the second postulate says. Now what about the third postulates? Postulate 3. Postulate 3 says that the summation of square of all the summation of square of all the summation of square of irreducible representations the summation of square of irreducible representations is equal to order of the group. Means what is said that this is the character tables. But it says that, let's say this is C2B, here E, C2Y, A sigma XY, sigma YZ, and here let's say this is IR1, this is IR2, this is IR3, this is IR4. Then here we have that 1 1 1 because that identity elements should be equal to order of the groups. Order is 4. Here order is 4. So this everyone 1 1. And now this we know that this is L1, M1, N1. This is L2, M2, N2. This is L3, M3, M4. So this is M3. This is N3. This is L4. This is M4. This is N4. Okay. So now what is said, this postulate says that the summation of square of any irreducible representations is any irreducible representation is equal to order of the groups. Means that after, if you add that any irreducible representation, either this if you square it, then also you get 4. This, otherwise if you do this, that means what I mean that either we can get this irreducible representation if you want IR1. So for IR1, irreducible representations are 1 square upon the summation of square of any irreducible representation. Let's say for IR1, irreducible representation 1, then 1 square L square m1 square plus n1 square, then also you get order of the group, that is 1 square plus L1 square plus m1 square plus n1 square equal to 4 we should get. That it means, or it may be not visible, so I will write here. It means that let's say IR1, for that irreducible representations are 1 square plus L1 square plus m1 square plus n1 square. This would get order of the group. Or also IR2, if you take any irreducible representation, this is 1 square plus L2 square plus m2 square plus n2 square. This also you get order of the group. Likewise IR3 also the same, if you do, then order of the group you will get, like that IR4. So this what the postulate 3 says. Okay, so if you add the summations of any irreducible representation, either IR1 or IR2 or IR3, then always you will get the order of the group. Okay, and the fourth postulate, that is very important, that postulates for what he says, that irreducible representations of any two, or we can write that multiplications or product, right? The product or multiplications of any two irreducible representations is always orthogonal to each other. What it means? Means that orthogonal means they are equal to each other. That means that is 0. It means that it says let's say any two, let's say IR1 into IR2 is orthogonal, means they are 0. Likewise, if I say IR1 into IR3, that is orthogonal to each other, means the product or multiplications of any two irreducible representations is always orthogonal to each other. It means IR1 into IR2 equal to 0. Orthogonal means 0. IR1 into IR2 equal to 0. Orthogonal means they are 90 degree, and the vector will give you the 0 value. So IR1 into IR2 equal to 0. Similarly, IR1, IR3 0. Similarly, IR2 into IR4 0, means any two irreducible representations, if you multiply it, then their results will give you 0. That's what the postulates for says. Okay, so these are the four postulates we should follow while writing that irreducible representations. So these four postulates we have to follow while writing the characters of irreducible representations. So what are the four postulates? First postulate is the number of multi-notations of character table is equal to the number of class of the point group. Means how many the classes will be there, that amount of irreducible representation notations symbols will be there. This is 4 is there, so these are 4. 1 2 3 4, not y5. If this is like for C3b, this is we have C3, E we have, after that 2 C3 and 3 sigma B. So how many classes? 3 classes. So here 3 classes will come. Sorry. 3, not 4. Because 3 classes are there, so 3 irreducible representations will be there. Okay, so here 4 is there, so 4 classes are there, so 4 symbols of irreducible representations will be notated. Okay, this is the first postulate. The second postulate what says that the summation of square of identity element is equal to the order of the groups. So this is the identity elements. So what are the characters is equal to the order of the group. The square of the summation of square of this identity characters is equal to the order of the group. So says that for C to B, we know that C and B, the order will be 2n. C and H order will be 2n. So if n is here, n is 2, then 2 into 2, that is 4. Okay. So the order will be 4. So if you are adding this square of this 1 square plus 1 square plus 1 square plus 1 square, that has to give the order of the point groups, that is 4, means here 4 has to give. That is the second postulate says. Okay, and the postulate 3 says that the summation of square of irreducible representation is equal to the order of the group. Means any irreducible representation, either IR1, IR2, any, if you add that irreducible representation, then we will get the order of the group. Either if you add this, you has to get order of the group 4. Okay, that we have explained here. And postulate 4 says that the product or multiplications of any two irreducible representations is always orthogonal to each other. Means IR1, IR2 equals 0, IR1, IR3, or we say that IR2 into IR3 equal to 0. They are orthogonal to each other. And one more points we have to note that IR1 is always have all 1 only, all 1s. Okay, means this IR representation, this always have the 1 1 1 for any representation for any groups. This is always 1 1 1. Okay, IR1 is always have all value as 1, all value as 1 for any point group. So this one also we have to note it. After that we will draw the character tables for a water, or we can draw for character tables for C3B or other character tables. So let's take the examples of water. So have did that C2B. So symmetry elements will come, that is E, C2Y, sigma XY and sigma YZ. So for classes of power will come IR1, IR2, 3 and IR4. Okay, and this is always 1 1, so 1 1 1, and this has to give the square of this has to give order of the group. So I have to put 1 1 1, because 1 square plus 1 square plus 1 square plus 1 square is going to give 4. Okay, so this is the order of the group. This much I have did. Now what I have to do, the next, so this one and this one, whatever the value, that if additions of this also has to give 4, if addition of this also has to give 4, this additions of this also has to give 4, because the postulate 3 says that square of additions of any irreducible representation is equal to the order of the group. Okay, so if I write here, that says A1, A2, A3, and like say A1, B1, C1, A2, B2, C2, A3, B3 and C3. What is say that this value also give, if you square of additions of this value also has to give 4, this square of additions of this value also has to give 4, this square of this value also has to give 4, and this square of this value also has to give 4, and this if I multiply, that has to get the value 0. That means IR1 into IR2, if the character multiplied, then product should get 0. Okay, so now what I do, E to Y, YZ. Okay, so this is 1 1 1, this is always 1, and for here this is 1 to get the order of the groups. So now this has left. So while writing here, I have to follow the power postulates. So that mainly that postulates for we will apply. This postulates for is importance. Postulates for, by applying postulate for, we will get the, means we will get the although all the postulates has to follow. So to get the value, postulate for will helps us more. So let's say that orthogonal to each other. It means what it says that IR1 into IR2 equal to 0. Okay, it means that IR1 is 1, or I can write here IR1 value into IR2 value, that should be get 0. It means IR1 is 1 1 1 1. Here I don't know what the value I taken, A1, B1 and C1. So here like A1, so this value is already 1 1, this is A1, this is B1, this is C1. So if we multiply, then I should get 0. Okay, if I multiplied with this, then I should get 0. So how I should get 0? Because this is already, this is one value, this is A1 value, this is B1 value, C1 value, this has to be equal to 0. So for that, what I have to do, and if we multiply with, if we add, okay, so that we will get the 0. So how we have to do, means here if I take this A1, let's say this is A1, if I take A1 as let's say A1 equal to 1. So if I put here, this is A1, so let's say I take here 1, then that for getting 0, this has to be minus 1, this has to be minus 1, because this is 1, this is 1, 2, this is minus 1, minus 1, minus 2, plus 2, minus 2 equal to 0. Okay, so if I take here 1, then another has to be minus 2, because this is getting plus 2. Okay, so to get the 0, this one also we can do, or also we can do here minus 1, then I can do here 1, and here also I have to do minus 1, this is also possible. Okay, or also you can do here minus 1 and 1, so that this minus 1, this is minus 1, minus 2, this is 1, and this is 1, plus 2, minus 2 plus 2 equal to 0. So any one we can take it. Okay, this one also you can do, or also you can, let's say keep it like this, any when there is no any conditions, we can do anything. Okay, so like that has to get the 0 value, and if you summation of square of summation has to get that order of the groups, and if we multiply that this two, then we get the 0, means IR1 into IR2 we should get 0. That is the conditions. Okay, now next what I will do, here I want, then here also I should get that orthogonality theorem I have to apply. That should be ortho means this one and this one if I multiply, I should get 0. Means multiply with additions, I should get 0. Or here if I put, so I should get plus 2 and minus 2, so that I will get 0 value. Okay, so here if I put minus 1, this is 1, and if I put 1, this is get minus 1, and here if I get minus 1, then this is minus 1, this is minus 1, minus 2, and this is 1, this is 1, 2, so it is getting 0. So this also you can put it. Okay, so and here I need, means plus 2 and minus 2 we should get. So here if I put this is already minus 1, if I put minus 1, then this is get 1, then 1, it is already become 2, so I need 2 minus 2, so here minus 1, here minus 1. It's not possible because this is minus 1, this is 1, 2, and this is 1, 3, this is only minus 1, so 3 minus 1, 3 minus 1, 2 we are getting, but we need the 0 value. I can't put like this. So if I put this is minus 1, if I put that 1, and if I put here minus 1, then minus 1, minus 1, minus 2, another is 1, 1 minus 1, another is minus 1 if I put, because 2 minus I has to put everywhere. Okay, so minus 1, minus 1, this is minus, this is 1, this is minus 1, this is minus 1, minus 1, minus 1, minus 2, this is 1, this is 1, 2, 0. Okay, so this one also you can do. Also, although another things you have to note that it should not repeat. See, this is the one case, in the middle minus minus, here one in the middle, another is last minus, here at the 2 minus. So this also we can like identify that they has to be not repeated. Otherwise if we repeat it, then this and this becomes same, right? So this and this should not be repeated, and if repeated, then that will not follow the orthogonality theorem also. If you calculate, then that may be problem with summation of square of summations equal to 4. That time we may not get, or that no, that time always you get, because minus minus is there, so 1 1 1, so if you square it, then always that will become 1, and total is 4 1 are there, so that always has to be 4. But the orthogonality theorem we may get the problem. Okay, so here, so this all things should not be repeated. So here all this 1, here minus 1, minus 1, here 1, this is minus 1, 1, minus 1, this is minus 1, minus 1. Here middle 2 are minus, here 1 at the middle, 1 at the last, here 2 are at last. Okay, so these characters I draw by using the 4 postulates. Okay, so postulates 1 I use to get this identity elements that is equal to the, so postulate 1 I use the postulate to how many irreducible representation, not symbols I have to draw, that I take help from this postulates 1. And postulate 2 I take that to get that elements of identity, that is the square of identity element is equal to order of the point groups. And postulate 3 I use that this everybody, every irreducible representations should equal to be the order of the group, that summation of square of all irreducible representations is equal to the order of the groups. And postulates 4, this is very very important, that the product of multiplications of two irreducible representation is always orthogonal to each other. Means that we have used that if you multiply by 2, and the square product of summation of product of any two irreducible representations has to be 0. Okay, that no, the product of, sorry, this is I have little bit wrong. The summation of product, we can write like that. This postulate is the summation of product of any two irreducible any two irreducible representations are always orthogonal to each other. Okay, so that's why if we multiply it by 2, then we are getting 0. Means multiply with that we have to additions. That means here the summation of product of any two irreducible represent for the characters, the summation of products of any two irreducible representation, any two characters of, here I should write characters of irreducible representation is always orthogonal to each other. Previously also right, from that time I not added the characters. If you add characters, then we have to add the summation, or also this the simple previous one also right, or the product of any two irreducible representations each any two representations are orthogonal to each other. Orthogonal to each other. This one also right. Okay. So by using that four postulates, we have to I have drawn the character table. Okay. So remaining the tables like we have done, this is C2B. Here we have done is C2Y, sigma YZ, sigma XY, and we have done that IR1, IR2, IR3, IR4 we have done, and this one we have done, that is 1 1 1 1. This is always 1 1 1 for all the irreducible representations. That's I've written here. IR1 is always have all value as 1 for any point group. Okay, that's why I write in 1 1 1. Now if I write this one, then I will write 2 minus 1 I needed, I'll write, and if I write 1 minus 1 here, minus 1, and this is will be minus 1 and 1. Okay. So not repeated anywhere. Okay, so this value means here all are 1 1, here 1 1 minus 1 minus 1, here 1 minus 1 1 minus 1, here 1 in middle minus 1, here 1 is here, 1 is here last. Okay, so this should not be repeated. And how these values we have to discuss that they has to be orthogonal. Okay, now also we have that 4 columns here. Also we have here columns 1 column, 2 column, 3 column, and 4 columns are there. Okay, so now that this IR1, IR2, IR3, IR4, so for representing these values we have to follow another 4 rules. So we actually by using the orthogonality theorems, GOT, we find that what are the characters of irreducible representations, and by using another 4 rules we find that what is the value of this irreducible representation symbols. Okay, so this is part 1, this is 2, so this is 3, this is 4. Okay, this is 4. So this one we know, you get it, this one also we get it, and this one also we calculate by using that 4 postulate, and to find this we have to use another 4 rules. Okay, so we have to follow the 4 rules. We have to follow the 4 rules to get part 3, that is irreducible that is symbol, or we can say Malkin notation of irreducible representations. Okay, so what are the power rules? That is part 3. This power rule, you have to follow the power rules. What are the power rules? So rule 1, what it says, that we will use this part 4 to calculate the part 1. Okay, so rule 1 says the the characters of identity is the characters of identity is one dimensions, then it is A or B, and if the character of identity is 1, it is 1, then A or B. If it is 2, then this is E, and this is 3, then that is P. That the rule says the characters of identity. Here let's say here that is 1 1 1 1, so this character of this identity elements is 1, then it means it is A we have. Okay, so sage for water, here this is C2B, and here we have E C2, and we have sigma xy, sigma yz, and here IR1 is there, IR2 is there, IR3 is there, and IR4 is there. So what it says, that rule 1, the character of identity is 1, then A or B we have to use, and if it's 2, then E is, and if 3 is, then T we have to use. Okay, so here everywhere is 1 1 1, this is 1 1 1, so this, the character of identity is everywhere 1, so here we have to use either A or B. Since here not 2 and 3 is there, so this will not come. So here we have to use either A or B, either A or B, either A or B, either A or B. Okay, this is the rule 1 says. And rule 2 what says? Let's discuss about of rule 2. This is rule 1. This is rule 1, and let's say this is rule 1A. Okay, another is rule 1 only, that is B. Rule 1B, what it says, that if a principal axis is symmetric, then use if principal axis is symmetric to the characters of irreducible representations. IR means irreducible representations. These are all irreducible representations. So the characters of irreducible representations with respect to principal axis with respect to principal axis is symmetric. is symmetric. Symmetric means positive you will get. Okay, it's symmetric, then use A. Then use A, and otherwise B. Okay, so if this is the principal axis, so what are that? We say this is 1, this is -1, this is -1, this is -1, this is 1, this is -1, and let's say this is -1, this is -1, and 1. So any value we can use, that should not be repeated. Okay, and they has to be orthogonal, we can calculate. So main thing that we have noticed is that they should be repeated, then it must be correct. Say -1, -1, here -1, -1, here -1. So no repetition is there, it is correct. Okay, so what is look that here the C2, this values, if it is positive, then we have to use A. Okay, so here C2, on the basis of C2, this is the principal axis here for water. Principal axis is water. So water structure, how it will do, I have already discussed. H1, let's say this is H2, and our axis is like this, X, this is X, this is Y, and this is Z. So I am passing the C2 axis like this, C2Y. So this is the principal axis. So principal axis, if it is coming 1, then we have to use A, not B. Okay, so principal axis 1, so I will use A. So if this is also again 1, then A will use. So I will use A. Okay, here this is minus means if I get if the principal axis is symmetric, means if it's getting the positive value, then I will use A, otherwise B, means if I get it negative, then I will use B. It means that minus it represent the asymmetric. So if the principal axis is negative, then that is asymmetric. On that time I will have to use B. Okay, so this is negative, I will use B. So this will be B, this will be B. Okay, so this one also we can show. We can say that if principal axis is positive, that irreducible representations. If positive, then we will use A, and if the irreducible representation is negative, then you use B. And this this positive shows that symmetric, and this negative shows that asymmetric. Okay, so this value we get, otherwise B. So this is the rule 1. Okay, let's discuss for rule 2. So what the rule 2 says, now we have discussed about a principal axis. Now the subsidiary axis. Irreducible representations are symmetric, means that is positive value with respect to subsidiary axis, then what we will have to use, we have to use 1, and this is, and if irreducible representation, I will write here IR, if irreducible representations IR are asymmetric, asymmetric means negative with respect to subsidiary axis, then I will use 2. Okay, so irreducible representations means these are the irreducible representations. So if this is -1 +1 -1, it means this is negative, this is positive, this is positive. So if these are positive with respect to subsidiary axis, then on that time that is 1. If it is negative with respect to subsidiary axis, here subsidiary axis is not there. If it is present, then that will going to give 2. If it is negative, if it is positive, then that will going to give 1. Okay, so here that subsidiary axis is not there, only C2 axis is there, one axis is there. So if subsidiary axis is absent, then take the molecular plane. Then take the molecular plane as subsidiary axis. Okay, so here subsidiary axis is absent, so molecular plane is taken as the subsidiary axis. So molecular plane is, this is my xy directions, this is xy, so this is my molecular plane. Okay, so with respect to molecular planes, what are there? This is 1. If it is positive, then that is 1. If it is negative, that is going to be 2. If it is positive, then that is going to be 1. If it is negative, then they are going to be 2. Okay, so if subsidiary axis is there and if the irreducible representation is positive with respect to subsidiary axis, if subsidiary axis is not absent, then molecular plane I have to put 1. Okay, this is the rule 2. So likewise I put, now I will go for rule 3. So for rules we have to follow rule 3. What the rule 3 says? Rule 3 says if center of symmetry is present, if center of symmetry is present in the group, if center of symmetry is present, then irreducible representations with respect to center of symmetries is asymmetric, is symmetric first. Is symmetric means positive, is symmetric, then right for center of symmetry what we are doing, either U or G, these are the notations. So if that symmetric, then positive means first in the alphabet first G will come, after that U will come. Okay, likewise you can remember. So if positive means first G will come. Okay, means for remember that is G. And if it is representation with respect to center of symmetry I is asymmetric, then U will come. Okay, so if the center of symmetry is present, then irreducible representation means this representations, if I is present with respect to, if it is positive, then G will come, if absent, then U will come. Okay, so for our case here that is not there, so we will simply, so we will discuss the examples. Like if I said C2H, okay, C2H, this is the molecules, like here is H, let's say C2H molecules. I will draw here. Let's say this is H. Let's say here Cl, here Cl. Okay, so in these molecules, so I is there, and also in these molecules, what things are there? Look it out. Here we have E is there, and C2 is there. If I do that C2, then this will get rotations, or we can take simply examples of for trans water. Okay, I can take water. This is H in these directions, H in these directions. This is the here I is there, and also here C2 is there, and here E is there, and I is there, and sigma H is also there, because C2 is in these directions, and C2 is here, C2 is here in these directions, and molecule says sigma H also present here. Like we can examine that. This is the molecules, like we can draw. Water is there, one is this directions. Here suppose one bond is there, then if I rotate by C2 axis, then 180 degree if I rotate, then we can rotate like this. This same molecule, see this molecules 180 degree rotations. I'm rotating like this. Okay, this directions is above, this is going like this. See this directions, I'm rotating from here, then what is going 180 degree rotations, this directions, this directions. Okay, so C2 is there. After that, what is there? Here I is there. Okay, and I am applying that C2 by these directions, then sigma H is there, sigma H is there, C2 is these directions, C2 is I am applying from this direction, I am passing that threads, so I can apply C2 also in these directions, and if I rotate, then it's good. And as H is that here the molecular plane cutting to all, then this will get perpendicular, means sigma H is there. Okay, so sigma H there, so this is E, C2, I, and sigma H. Okay, so here that 4 classes, so I will do IR1, IR2, so IR1, IR2, IR3, and IR4. Okay, so this is always 1, 1, 1, 1, and that C2H, the order is also that 2n, so 2, 2, the 4, so this also get 1, 1, 1. Okay, now this the principal axis is C2, so here also same characters will come, because the order will be has to be 4, so this is I can write 1, minus 1, minus 1, I can write 1, minus 1, 1, minus 1, I can write 1, minus 1, minus 1. Okay, so same as like that, and here that I is there. Okay, so first thing is that if that C2, if E is there, and if it is 1, then A or B only come. So here A or B, A or B, so here A or B, here A or B, because identity is 1. 2 is there, then the chances of E, or if it is 3, then chances of P, because here identity is always 1, because on the 4 is order is 4, so to get 4 all has to be 1, so only 1 means A or B. Okay, now next is C2. If C2 is so rule 2, if C2 is, if principal, this is principal axis, if principal axis is 1, then always what rule 2, what says the rule 2, So rule 1 is this, and rule B say that the character of IR with respect to principal axis is symmetric positive, then use A, otherwise B. Okay. So anything wrong with it? 1 minus 1. Principal axis is this. I think something get wrong. Yes, this one I repeated. Okay, so I show the repetitions is not allowed because that this and this value get same, right? So repetitions will not allow. Okay, so here that then I will put here minus 1, here minus 1, this is 1. Okay, now I see. So C2, if it is positive then only A, and if negative then B will come. So here this is positive, this is positive, principal axis, this is positive, then here only A. So I will remove B, and if it's negative, principal axis is negative, irreducible representation, these are irreducible representation, with principal axis is negative then B. So irreducible representation here negative, with principal axis then this will come B. Okay, after that rule 2 what it says, irreducible representations are symmetric positive with respect to subsidiary axis, then I. So here subsidiary axis is not present, so we will not go. Next we will go to, and sigma h, principal axis molecular plane is here sigma h. Okay, so here that molecular plane is sigma h, but sigma h also the rule is there, so we will not go that. And I will go, see I, so center of symmetry, if it is positive then G, if negative then U. Okay, so here I is positive then this is G, this is negative then this is U, this is positive then again this is G, negative then again this is U. Okay, and let's discuss the third rules, the last rule, that is 4 rules. Rule number 4. What the rule number 4 says, that irreducible representations with respect to sigma h is symmetric, then we will get sigma h is respect, then we will get this one symbol. And if irreducible representations with respect to sigma h is asymmetric, that is negative, here this is positive, then we will use 2 symbols. Okay, these symbols. Okay, so here that sigma h we have, and this is positives, then 1 symbol we will use, 2 negative, here negative, so here double symbol, here also double symbol, here positive, then 1 symbol. Okay, likewise the 4 rules we have to follow while doing the notations of Amalki notations of irreducible symbols. Okay, so for getting these values we have to follow these 4 rules. Rule 1, A, that if dimensions identity elements is 1 then A or B, and it is 2 then E, it will be 3 then T. And A or B, how will you decide? By taking rule B, rule 1 B, that the character of irreducible representation with principal axis is symmetric. So these are the irreducible representations. Okay, these are the irreducible representations. So this irreducible representation with respect to principal axis is positive or negative. Likewise, we are doing this notation. So here the characters of irreducible representation means these characters with respect to principal axis. This is principal axis for here. It's symmetric. Then if it is positive, then you use A, otherwise if negative then you use B. Okay, that is the rule 1 B says, and rule 2 says irreducible representations are symmetric with respect to subsidiary axis if present, otherwise molecular plane, then 1, and if irreducible representations are asymmetric with respect to subsidiary axis, then 2. So here for waters we don't have that subsidiary axis, but molecular plane we have. So if it is 1 then 1, if it is minus 1 then it is 2. Okay, this is the rule 2. And rule 3 says that if we have that center of symmetry and it is symmetric, irreducible representation of symmetric with respect to this, then G. Okay, that we take here. If this is the I, this is the center of symmetry, this E representation values, if these values are positive with respect to this, here this is positive with respect to this, then we use G. Here this irreducible representations values for the characters, these are the irreducible characters. So we are doing this notation with respect to this irreducible representation characters. If these characters with respect to this I, with respect to H, with respect to principal axis, with respect to E, what are they? Like if here for center of symmetry, this irreducible representation, this is 1, with I is positive, that's why G is negative, that's why U, it is positive, G is negative, U. Okay, this is the third. And fourth is that irreducible representation with respect to sigma H. It's symmetric, then this symbol. If it is negative, then double symbols. Okay, likewise. So this is all about of that these values we have discussed, and this one also we have discussed. Now that in a character tables, another thing is that here C2B, here is C2 Y sigma YZ, and here let's say, or I will not draw because if I drawing then all things I have to maintain same. If I change one things, then all I have to change accordingly. So whatever you are taking that, see if I am doing this one, for this, what I do that here, okay, XY YZ, okay, I can do that XY and YZ. So here C2B, to do that E C2Y sigma XY and sigma YZ, and irreducible representations are what we have get. Let's say this is IR1, let's say this is 1 1 1 1, this 4 characters we have. Quickly drawing IR1, IR2, IR3, IR4. So this is all are 1 1 1 because order is 4, this order is 1 1, and likewise if I put 1, here minus 1 minus 1, and if I put minus 1 1 minus 1 1 minus, then I have to put minus 1 1. Okay, so these values, that is always A or B, and this is 1, so here A, this is 1, also here A, this is minus the B minus the B. Okay, and this planar, this is the principal axis, this is the molecular plane. So this is 1, so this is 1, this is negative 2, this is 1 negative, this is 2. Okay, so another so 4 columns, this is column 1, this is column 2, this is column 3, and another columns I need, this is column 4, and this is row 1, this is row 2. Okay, so for these columns 3 and column 4, this have the rotational axis or translational axis. So these values, any x, y, z axis, so that values actually we no need to memorize, that is already given in the exams. Let's look these values. So here will be a rotational axis and rotational or translational axis will present. Here that quadratic values will be present. So here like z for water, and here like rz, and here like x, ry, and here y, rx, and here the quadratic values, quadratic, that is either here x square, y square, and z square, and here xy and xz and yz. So these values we will discuss how these values come in next class. So although this is not important, only important is you have to draw this much. Also this also the fully that character table is given to you, then they only ask that after giving character table they ask the questions. So character table is given in the exam, so no need to worry. So only you should know that how it is come. Okay. So after discussing in this, now if you discuss about of C3b, let's discuss about of C3b. Then what are the characters it have? E, 2C3, 3 sigma b. Okay, so 3 classes, so 3 representations I will do, that IR1, IR2, IR3, and this is always 1, 1, 1, and this is going to be order of the group. So C3b, the order will be 2n, so n is here 3, so 2 into 3, that is 6, order should be 6. So to getting the orders, I have to square of this these elements. So let's say this is A1, B1, this is C1, this is A2, this is B2, C2. So this the square of identity elements, the summation of square of identity element is equal to order of the group. So 1 square plus A1 square plus A2 square, which has to be the 6. And the dimensions, this identity elements, this is actually what said, this is the dimension, and the dimensions never be 0. So always I have to put 1, 1 only, never I will put -1 or -2 like that, because the dimensions always positive, like height is always positive. Okay, so this is 6. So here I will put always the positive value. So if I put 1 square, and if I put 1 square, if I put 2 square, then this is 1 plus 2 is 4, then we will get 6. So we can put this 1 and 2. Okay, we will get, after that this value has remain, then we have to follow the orthogonality rules also, that this value has to be order of the groups. If the square of this value also has to be order of the groups, that is IR2, I can say that 1 square plus 2 square plus square, that it has to be 6. Okay, that we said na, that rule number, sorry, postulate 2 or 3, we said that the characters of irreducible characters of any irreducible characters, the summation of the square of summations is always order of the groups. Okay, so if the summation also always has to be order of the groups, and that irreducible representations of any two, the product of any two irreducible representations always orthogonal, means the product value is always 0. So I can write into 1 IR1 into IR2 is actually 0. So, and here that coefficient is also there, so this coefficient also we have to multiply it only once. Okay, so what I'll do, 2 into IR1, that characters, let's say here 1 into B1, So here the coefficient is 1. So here coefficient, this is coefficient 1 into this value 1 into this value into 1 plus here 2. So this is the square. Okay, so 1 and this is 1, so this is 1 square and this is again 1 square plus this is 2 into this is 1. Sorry, I have to review this. This is first coefficient into this whatever this values, let's say this 1 square, after that this again 1 square summation, this again this is 2 coefficients into this is 1, that is 1 square and this is b square. Okay, and coefficient into this is 1 square, this is square, this has to be 0. Okay, so this one if we write, then coefficients for the above is how much? This is 1 coefficient, so 1 upon this is 1 square, this is 1, this is also 1 square upon 1 plus coefficient for this is 2, so 2 into 1 into b1 square plus this is 3 coefficient, so 3 into this is 1 into c1 square, that has to be 0. So I can say that this is 1 into 2b1 square plus 3 c1 square has to be 0. So to get this value 0, what the value I have to put? So I want to value the 0, so this b1 value has to, I want to 0, so what the value I have to put? c1 square. So if this is, if I put the 0, then let's say this is minus 1 into 3, let's say this is 1 into 2 and this is 1, then what you will get? 1 plus 2, this is you get plus 3. Sorry, that not square product, this is not square, simply the values, square you will not take. Okay, sorry. Okay, square you will not take. Okay, so this is 1, this is 2, then this is minus 3, then this is 0, so we have to take here minus 1 and here 1. Okay, so we see that this is 1, this is 2, 2 1 1 2 1 2 3, and this is 3 1 3 minus 3, that is equal to 0. And here what you have to take, if I take 2 3, so if I take this here, I will take minus 1, if I 0, then this is 0, this is minus 2 and 2 2, this is 1 1 2 0. So this is the calculable. So we have to follow the orthogonality theorem and this value, then okay, this is IR1, this is IR1 and IR2, IR1 IR2 and IR3. So first principal axis, this is 1, first identity, so this is 1 1, so A or B, here I have to use A or B, and here 2 means E will come. Okay, now this principal axis is C3, so here that what is there, 1 1 minus 1, so if it is 1, then this is A, and it is 1, then this is A, and this is minus 1, then for this A. Okay, now that next we will look on if that subsidiary x is not there, then we will look the plane. Okay, so here sigma b is there, and this is 1, then this is 2, then this is 2. So we will discuss more on it in next class. Today up to this, thank you.